All righty, lads and ladies, welcome back to the wonderful and wild and weird and wacky world of calculus. I hope everybody had a nice spring break, not too much trouble. And I hope we're all able to do a little bit of mathematics over that break. I did see, I think, just one study guide submission this morning, which is okay. But I do want to remind you that the sooner you submit your study guide work in Canvas, the sooner I can get it marked and get you some feedback. Definitely, you would ideally have that before the test. You know, I will certainly take the study guide on the day of the test if you choose to submit it on Friday. But if you're able to submit it, say, before Thursday afternoon, then I'll be able to get you a little bit of feedback on that, which I find generally is very helpful for the test itself. So let's get in here and start doing the thing. We do have one more bit of stuff to talk about before the test, and that is this. It's an application, right? So what we're going to look at today is optimization. We've studied min and max problems quite a bit, and as you know, calculus often finds applications in real life situations. One of the more common families of real life situations where we apply calculus is taking those min-max tools that we have and applying them to functions that describe real world things like profit. You often want to maximize your profit. So finding a function that expresses the profit a company makes in terms of the number of units sold can be a useful tool, because then you can take the derivative and find the max. There's a bunch of things like that. So let's dive in here. This is MAC2311. The section number is 004. This is a Calc 1 class. And the date today is 3/14/22. It's Pi Day. So today, we're going to talk about applied optimization. And I forget the section number, honestly, off the top of my head. I think it's 4.7. And your textbook just calls it optimization problems. So this is section 4.7. And this is the last section that's going to be on the test. I will be very gentle with you on the test when it comes to this section, because I know that you've had less time with it. Ideally, I would give you a full week between introducing material and testing you on it. So the test problems from this section will be gentle, but it will be on the test. This is the appropriate place for it. If we push this to test 3, it really doesn't fit with the flow at all. What we're going to be doing here is taking some word problem, generally, trying to translate it into the calculus problem of, like, here's a function, find the max, or here's a function, find the min. And then solving that calculus problem and interpreting the result in the context of the real world situation. It's kind of similar to related rates in this way. I can give you a bit of an algorithm for this, but I think it'd be better to just start with an example. So let me go ahead and transcribe this example. We got 2,400 feet of fence to fence in a rectangular field along a river, needs no fence along the river, maximize the area. So a farmer, 2,400 feet of fence to enclose land in a rectangle along a river. We want to find the maximum area she can enclose. So as you may have seen there, the textbook suggests, and I agree with this, the first thing you should do with these problems is draw a picture, just like with related rates. So here's my river. And I'm trying to enclose some land over here in the shape of a rectangle. And although I didn't write it here, you saw in the problem, they say you don't need any fence along the river, right? I'm trying to keep some cows in or something. They don't swim well, so I'm not terribly concerned about anything escaping across the river. I just want to make sure that I'm enclosing as much land as possible along this river. It's up to us to label things with variables and to find the algebraic relationships between those variables. And we want to do this in a way that is intelligent. So the area I'll call A. This dimension I can call X, and this dimension I can call Y. And because this is a rectangle, this fellow over here is also X. Our goal is to maximize the enclosed area. So we should find a formula for the area. Well, the area of a rectangle is just its like length times its width, right? So that's X times Y. And this is the thing you're trying to maximize. What we see here, though, is that this is sort of most naturally expressed as a function of two variables. And this is something that you'll see in a lot of these problems. What's here to help us out is something called a constraint. So you'd say we want to maximize that subject to the constraint. Obviously, if I had infinite amount of fence, I could enclose whatever size area you want, up to, you know, the area of the planet, I suppose. But I don't have an infinite amount of fence. There is a constraint. I only have 2,400 feet of fence, which means that the total amount of fence I use, this plus this plus this, has to equal or can be no less than, no greater than 2,400. I think it's fairly intuitive that if I'm trying to enclose the most amount of area, I should use all my fence. If I've got fence left over, I could have used that to enclose more area. So my constraint here is that X plus Y plus X is 2,400, or 2X plus Y equals 2,400. These two equations together will give us everything we need. So first I want to make sure, are we comfy with the picture? Are we comfy with the thing we're trying to maximize? And are we comfy with the constraint? Comfy with where all that stuff comes from? Okay. From here, the name of the game is to get this thing into a form where I can differentiate and find the max. In order to do that, I need to have a function of just one variable. So I can solve my constraint either for X or for Y, then plug that back into the function I'm trying to maximize. That will give me a function of a single variable, which I can differentiate and find the max on. So if we subtract 2x from both sides, I get y equals 2,400 minus 2x. Plugging in 2,400 minus 2x for y in the area equation gives me a equals x times 2,400 minus 2x. So my goal is to maximize this function. All right, I want to find the max area that our farmer can enclose. Here's a function for the area. So if I find the max of this function, I have answered the question. It might be useful to go ahead and distribute that x so I don't need to use the product rule to differentiate. So I get 2400 x minus 2x squared. Some light starting to come through here. So lighting a little bit. So now a primed, the derivative of this area function is going to be, let's see, derivative of 2400x, that's 2400 minus the derivative of 2x squared is 4x. So the critical numbers are coming from this thing equals 0. And there's only one of them. If you set this equal to 0, let's see, 2400 minus 4x equals 0. That means 2400 is equal to 4x, which means, let's see, 24 divided by 4 is 6. So this is 600 equals x. So I make a number line for a prime, just like we were doing in section 4.5, 4.3. There's only one critical number here. It's at 600. If I look to the left of 600, then a prime will be positive, right? You plug in 1, then you get 2400 minus 1. A prime is definitely positive over here. And if I look to the right of 600, say 700 or something like that, 2400 minus 4 times 700 is 2400 minus 2800 is negative 400. So in particular, we would be negative over here. You do want to think about what is a reasonable domain for this thing. That's important. So it's worth noting here that to the left of 0, I'm not interested, right? I'm not building a paddock with 0 feet of fence. And to the right of 2400, I wrote 24,000 here, didn't I? It's 2400, sorry. To the right of 2400, I'm also not interested because I only have 2400 feet of fencing to play with. So when you get to this step and you're making your number line, I think it is wise to consider your domain. So the values of x for which this thing makes sense are 0 to 2400. But I'm increasing everywhere to the left of 600, decreasing everywhere to the right of 600. That means this must be a max. So the area is maximized when x is equal to 600. But that's not the question they asked, right? X is this length. X is this length right here, right? This length right here. They asked, what is the maximum area we can enclose? So to find that max area, we need to compute the area when x is 600. And we can do that by plugging into here. So the max area is going to be when x is 600. And if I plug into this area function, I see that that is going to be 600 times 2400 minus 2 times 600. And that's 600 times, let's see, 2 times 600 is 1200. 2400 minus 1200 is 1200. And then what do I get here? 6 times 12 is 72. And so that's 72 followed by 4 zeros. Oop, come in. 720,000. And the units here would be square feet, right? We're measuring all these distances in feet. This would be feet squared or square feet. And that's it. So it really is the same stuff that we were doing before. You're still just trying to find the max of some function on some interval. The challenge is interpreting the real world situation. Before I move on, questions on this solution? Okay, then, before we look at the next problem, let me go ahead and discuss, now that we have a feeling for what the hell it is we're trying to do, some procedures that are helpful here. So to solve steps, to solve optimization problems. I would say first, definitely draw a picture. Right, just like with your related rates problems, it's a real world thing. And if you're going to impose mathematics onto the real world, it's always nice to start by drawing a picture, trying to model the thing. Then you're going to label or assign variables to the relevant quantities. So like the lengths of the field and the area of the field were the relevant quantities in the last one. 2 of those lengths were the same, so I called them both x. 1 of those lengths could be different, so I called it y. And of course, the area can change, so we want to make sure that we assign variables to all the relevant quantities. And then you're going to identify the function or expression we want to maximize or minimize. Right? Sometimes you want to minimize things, like minimize the amount of material or minimize your costs, that sort of stuff. Then you're also going to identify a constraint. Any possible constraints. If there is a constraint, solve that constraint for one of the variables and plug that into the expression we want to maximize. And then from here, it's a straight up calculus thing, right? Take the derivative, find the min or the max. There is also one theorem in this section, which I think is kind of cute because it's not in any way native to this section mathematically, but it is useful in a lot of these problems because it saves you time. Generally, the min or the max that we're looking for here is going to be an absolute min or an absolute max on some interval. And so the theorem, let me state it exactly as it is in your book, basically says if there's one min or one max, if you're increasing to the left of a critical number and decreasing to the right of that critical number, and there's nothing else going on, then that has to be an absolute max. Yeah, here it is. So here's the way they say it. Suppose C is a critical number for a continuous function f defined on an interval. So I'll go ahead and transcribe this the way they do it. Suppose C is the only critical number for the continuous function f on an interval, I'll call it I, then if f primed of x is negative for all x less than c, and f primed of x is positive for all x greater than c, what can we deduce? Well, if f prime is negative everywhere to the left of c, that means I'm decreasing everywhere to the left of c. And f prime is positive everywhere to the right of c means I'm increasing everywhere to the right of c. So the conclusion here is then f has not just a local min, but an absolute min at x equals c. And the other kind of way of turning around the inequalities, if f primed of x is positive for all x less than c, and f primed of x is negative for all x bigger than c, then f has an absolute max at x equals c. Basically what this says is if you've got, if you only have, it's not a nice way to simplify this. If you're increasing everywhere to the left of c and decreasing everywhere to the right of c, that means you're going uphill, 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 downhill, 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 and you never did anything else. So the top of that hill is the highest you ever got. Or if you're going downhill, 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 then uphill, 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 and you never do anything else, meaning you never turn around again, then that min, the bottom of that valley, is the lowest you ever got. It's just a bit of a time saver. It lets us go from the number line work that I did for you on the previous page to the conclusion that your max is not only a local max, but an absolute max as well. This is so intuitive that you probably don't need to be told it. And seeing it here, I'm not sure makes it any clearer, but it's a theorem in the section, so we should discuss it. All right, let's try another problem. Let's try to use this theorem and those steps to solve another little optimization problem. This is a good one. So I'm going to make a cylinder can, a cylindrical can, and I need it to hold 1 liter of oil. I want to find the dimensions that minimize the cost. Now, of course, there are some weird assumptions baked in when you phrase the problem that way. So I'm going to change the phrasing just a little bit. I'm going to say find the dimensions that minimize the material used to make the can. Now, I actually had an honors student in my Calc 1 honors class last semester do a project on this, and it was pretty cute. He went out and measured a bunch of cans, right? Like not just oil cans, but like soup cans, other cans. And what he found was that the majority of them do have dimensions that correspond to the solution of this problem. So the vast majority of food manufacturers, anybody who puts shit in cans, actually follows the result we're going to get here. And the numbers are kind of weird. You'd be a little surprised. So where do I begin? What's my first step?
Draw a picture.
Let's draw a picture. So, all right, here's a cylindrical can. Its top is a circle. It's got straight sides. And its bottom is a circle, same size circle as the top. Here's my cylindrical can. What are the relevant quantities that I need to assign labels to?
Its volume is 1 liter.
Yeah, the volume, right? Let's call the volume V. And we know that V is equal to 1. I'll just write it as 1 rather than 1 liter with the assumption that we're going to use SI units everywhere here. So liters is the SI unit for volume. Some other things I might label here. The radius of the can. Right, and that's the same radius down here. And also the height of the can. Because the way you find the volume of a cylinder is in terms of these guys, right? Now, the formula for the volume of a cylinder, you take the area of one, just like when you're finding the volume of a box, you take like the length times the width times the height. If you think about what that is, that's the area of a cross section times the distance that that cross section moves through the solid. So if you take the area of this top circle and multiply it by the height, that gives you the volume. So on the one hand, we know V is equal to 1. On the other hand, the volume is going to be pi r squared, that's the area of the top, times the height. Am I trying to maximize or minimize the volume though?
No, the radius and the height.
Sort of. So I'm trying to minimize the material used in the can. What sort of statistic on the can tells me the amount of material you need to make it up? Right, the can's not solid metal, it's empty inside, right? It's holding oil. So what
Would it be the surface area?
Yeah. So the other thing that we need here is the surface area. Let me call that S. So the volume we'll call V, the surface area we'll call S. This is the thing I'm trying to minimize. Now, finding the surface area of a can requires a little bit of creativity. Imagine I pop the top off. I pop the bottom off. And then what's left over, I'm going to cut and unroll the middle piece. So this is my top, this is the bottom. And this is the middle piece here that I've like cut and then unrolled. So it's like the wall of the can. The surface area, the total surface area of the can is this area plus this area plus this area. So the area of this guy is pi r squared. He's a circle. Area of this guy is pi r squared. He's that same circle of radius r. What is this dimension? And what is this dimension?
The height times the diameter.
Almost. This one is the height, but this is not the diameter. Remember, I'm cutting and unrolling the whole cylinder. So the
Oh,
diameter
the
is
circumference.
yeah, it's the circumference. And that's always 2 pi times the radius. Right? It's like the circumference of the circle that you get when you look straight down from the top. So my surface area altogether, what do I have? I've got pi r squared plus pi r squared. That's 2 pi r squared plus 2 pi r times h, right? Length times height. So this is the thing I want to minimize. This thing, the volume, since we know the volume is 1, and on the other hand, we know the volume is pi r squared h, then we know that 1 is equal to pi r squared h. This is my constraint. So I want to minimize this function s subject to this constraint. All right, this is all the sort of creative work. So let's pause for a minute. Are there any questions we'd like to ask at this stage? We're all comfortable with where the volume expression comes from and why I'm setting that equal to 1? And we understand why that's the constraint, right? Because they told us the can has to hold 1 liter of oil. I don't have any control over that. The volume must be 1 liter. The thing I have some control over is the height and the radius. And I'm trying to pick the correct height and the correct radius to minimize the material. And the amount of material that goes into a can is just the surface area, right? The wall thickness matters here too. It's neither here nor there. We'll assume that the wall thickness is very small and constant. We don't have to fuck with it. In real life, though, how thick the material is would also matter. Okay, so I've got my thing I'm trying to optimize. In this case, I want to minimize it. And I've got my constraint. What's my next step?
Solve for a variable.
Yeah, we take our constraint and solve for one of the variables, right? I cannot differentiate and minimize this right now because it's got 2 variables in it. But if I'm able to get rid of one of those variables, like r shows up twice, so maybe that's not the thing to get rid of. H only shows up once. So if I can get rid of this h, then this will be a pure function of r. And I can work to minimize that by doing the normal stuff, take derivative, number line, blah, blah, blah. So if I solve this for h, so I'm going to say solve the constraint for h. So what does that give me? That gives me 1 over pi r squared equals h. And then I'll plug this in into my surface area. that gives me S equals 2 pi r squared plus 2 pi r. And now instead of h, I'm going to write 1 over pi r squared. So now this is a function just of the one variable, r, and that means I can do all the calculus things that we like. We can differentiate and find the mins and maxes. I think, like the previous one, it's wise to clean up a little bit of algebra here. I don't want to differentiate this with like a combination of product and quotient rules or anything like that. That would be silly. The pi's cancel, right? And then r over r squared, that cancels also. This is 2 times 1 over r. So simplifying that a little bit, I get S equals 2 pi r squared plus 2 times 1 over r, or plus 2 over r, if you prefer. This means that S primed, the derivative here, taken with respect to r, is going to be 2 pi times 2r, or 4 pi r. The derivative of 1 over r, who remembers how to do that? No, it's been a nice long spring break here, so I'm not making fun of you. I just want to see if we remember. We can write 1 over r as r to the -1. And then when I differentiate that, I get -1 times r to the -2, which is -1 over r squared. So the second piece here, this plus 2 times 1 over r, is going to become minus 2 over r squared. And I need to find critical numbers, right? My goal is to minimize this. So to find the critical numbers here, I'm going to have a common denominator. I want to find anywhere this thing is equal to 0 or undefined. Clearly, this is undefined at 0. To find out where this is equal to 0, I'll have a common denominator. So 4 pi r minus 2 over r squared. If I multiply by r squared over r squared, that becomes 4 pi r cubed over r squared minus 2, minus 2 over r squared. Oh, 20, that's just a scribble. And that is 4 pi r cubed minus 2 over r squared. So again, definitely undefined at 0. And where is it going to be equal to 0? Well, to find where a rational function is equal to 0, you set the top equal to 0. Can add 2 to both sides. Divide both sides by 4 pi. 2 divided by 4 pi is 1 over 2 pi. And then you can take the cube root on both sides. So we get the cube root of 1 over 2 pi. When I said there are some strange numbers here, this is what I meant. Right? This is kind of an odd number, and it's not something that you would necessarily expect to show up in in a problem like this. But there it is. So that's your critical number, right? Technically, there's two critical numbers. These are r equals 0 and r equals 1, sorry, the cube root of 1 over 2 pi. So I draw a number line. This is the number line for s primed. Put 0 over here, and the cube root of 1 over 2 pi here. Definitely not interested in anything to the left of 0. I cannot have a negative radius. In theory, my radius could be as big as you want. I just have to make the height smaller and smaller. So there's no upper bound here. There's no largest value for r that makes sense. I could have a 1 liter can that has a 1,000,000-mile radius. It's just going to be a very, very, very short can. So I'm interested primarily in what happens here. Am I increasing here, decreasing here, decreasing here, increasing here? What's the deal? A few ways to see this. If you plug a large number in for r, like 1,000,000, then the top is like 4 pi times 1,000,000 cubed minus 2. And that is definitely, because the power up here is larger, going to be larger than 1,000,000 squared. But the safe bet is to use some test points. So we'll be patient here. 1 over 2 pi is a number smaller than 1 for sure, right? Because 2 pi is bigger than 1. So the cube root of 1 over 2 pi is smaller than 1. That means we can test r equals 1 to the right here. If I plug 1 into s primed, I'm going to get 4 pi times 1 cubed is 1, minus 2 all over 1 squared, which is 1. So that's 4 pi minus 2. Now, is that positive or negative?
Positive.
Definitely positive, right? 4 pi is like in the neighborhood of 12. So this is for sure positive. The root here is a multiplicity 3 root, right? This is like some constant times r cubed minus some other constant. So you could deduce using multiplicities that were negative in here. Or you could do some calculator work and find some number in here that is testable. Let's see here. Actually, I'm not going to use this thing. I hate this thing. So my cube root, let's see, of 1 over 2 pi is that raised to the 1/3 power. It's like 0.54. So I could use 1/2. I could test r equals 1/2. 0.5. S primed of 1/2. This ain't going to be pretty, but let's see what we get. That's going to be 4 pi times 1/2 cubed is 1/8 minus 2 divided by 1/2 squared is 1/4. Zoom in a little for you here. 4 pi times 1/8 is pi over 2. So I have pi over 2 minus 2 divided by 1/4, which is 4 times pi over 2 minus 2. Again, pi is in the neighborhood of 3. So pi over 2 is like 3/2 or 1.5. So pi over 2 minus 2 is like 1.5 minus 2 is negative, right? So we were correct. This is negative. So we are decreasing, decreasing, decreasing everywhere to the left of this critical number, increasing, increasing, increasing everywhere to the right of this critical number, which means that must be a min. Not just any min, an absolute min. So I'll say it like this. So S has an absolute min at R equals the cube root of 1 over 2 pi. So that's the radius which does the thing we need. A word of warning to you. On the test, and in your homework, but especially on the test, it's often the case that people get to this step and they say, okay, I'm done, without ever checking that the thing they found was a min. It's very important that you check that the thing you found is the thing you're looking for, right? If this was a max, then this is not what we want. We're trying to minimize the surface area. What I'm doing here is basically using the first derivative test from section 4.3, right? This number line, the increasing, decreasing to determine whether this is a min or a max. That's the first derivative test. You can use the second derivative test also. I'm okay with that, but you need to do something to check that what you found is in fact the thing you're looking for. If you skip this step, then I will not be able to give you full credit on a test problem. Okay. We found that the surface area is minimized when R is the cube root of 1 over 2 pi. Still not quite done though. They wanted the dimensions, plural, which minimize the material, which means we also need to tell them what H is. So when R is the cube root of 1 over 2 pi, we know H is, if you look back, we solved for H in terms of R earlier. Where was it? Shuffled it to the back here. Yeah. Earlier we solved for H in terms of R right there. So H is 1 over pi R squared. And if you plug in the cube root of 1 over 2 pi for R, you get 1 over pi times the cube root of 1 over 2 pi squared, which is a mighty strange number. But we can clean it up. The cube root of 1 over 2 pi is 1 over the cube root of pi. When you square that, you get 2 pi. So here, let me write this down. This is 1 over pi times 1 over 2 pi to the 2/3 power. So the cube root is the 1/3 power, and then I'm squaring that. And then a little flip and multiply, and you get 2 pi to the 2/3 divided by pi. Could you do more? Yeah. Would I expect you to do more? No. If you give it to me like this, will I give you full credit? Yeah. Would I prefer it like this? Also, yeah. So these are your final answers. You want to pick the radius to be the cube root of 1 over 2 pi and the height to be 2 pi to the 2/3 divided by pi. Now, I shit you not, go take your favorite soup can, bigger the better, right? Because this matters more with larger volumes, like a can of crushed tomatoes, one of the big ones, that sort of thing. Go take some food cans or oil cans or whatever kind of cans you can find at your local buy shit place, and take the ratio of the radius to the height. And you'll find that they match the ratio of the radius to the height here. Those cans won't be 1 liter. You find 1 liter cans, then they'll actually match these quite closely. Otherwise, take the ratio, divide the two, and you'll find that this matches. I think it's pretty cool. Questions on the procedure here, on any one of these steps? Okay. Not every optimization problem is a real world thing. There are some very fun optimization problems that are purely geometric. Yeah, this is fun. So like example 3 here, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. So it's a pure geometry thing. What we need here obviously is the distance from a point on this curve to the point 1, 4. That's the thing we're going to try to minimize because I'm looking for the point that is closest to that. Definitely, it is helpful to sketch the graph here. That is going to be your picture for this problem. Y squared equals 2x. You can do this a bunch of ways. If you learned how to work with conics more generally in your pre-calculus class, is a good place to whip that stuff out. Otherwise, you can think of this as x equals 1/2 y squared. So it's going to be the same as like y equals 1/2 x squared, just turned sideways. In other words, it's a slightly fat parabola that opens to the right. And the vertex is at the origin. You plug in 0 for x, you find out y is also 0. You can plot a few points, right, by plugging in like 2 for x, and then you see y is equal to 2. And the point 1, 4 is going to be right around here. I want to take an arbitrary point on this parabola. I'll start by just calling it x, y, but I will change that in a minute, and find a formula for the distance from that point to the point 1, 4. So I'll label that distance as d. And I can think of this point on the parabola 2 different ways. If I solve this for y, first observe that whatever this closest point is, it's coming from up here. It's not coming from down here. So if I solve this for y, if I solve this equation for y, I get y equals plus or minus the square root of 2x. And since I'm looking in quadrant 1 here, that would just be the square root of 2x. All right, so x, y, but y squared is 2x. So y is the square root of 2x. The other way I can think of this point, the x value here, if you solve this for x, would be 1/2 y squared. So I could call this point 1/2 y squared comma y. Same thing. And what we want to do is build up, build up a formula for this distance. And I'll have to pick one of these two ways of writing the point. So remember your distance formula. Says that the distance from one point to another, like distance from x1, y1 to x2, y2, is square root of x squared, x2 minus x1 squared plus y2 minus y1 squared. That's the formula for the distance between 2 points. Say x1, y1, and x2, y2. I'm going to use this formula where one of the points is the point 1, 4, and the other point is this arbitrary point on the parabola. And when it comes to the arbitrary point on the parabola, I have a choice as to whether I want to write it like this or like this. For my money, I would rather differentiate things with whole number powers of x, or with whole number powers of my variable, than square roots. So I'm going to go with this characterization of that point. Here's my distance formula. And this tells me that d would be the square root of some stuff. I'm just going to write d squared equals the stuff. And then I'll use this as x1, y1, and this as x2, y2. So x1 is 1/2 y squared. So x2 minus x1 is this minus the x value here, which is 1, all squared, plus y2 minus y1. Well, that's y minus 4, all squared. And then a nice trick here. If you want to minimize d, it suffices to minimize d squared. Right? In other words, I can minimize this thing, and that will minimize the distance. So observe that it suffices to minimize d squared. I don't need to worry about the big square root on the outside. In other words, if the thing inside the square root is small, then the square root will be small. If the thing inside the square root is big, then the square root will be big. So it's nicer to work in this form because then I don't need some big nasty chain rule thing, right? I could say, okay, d is the square root of this. I could take the square root on both sides and then directly work to minimize d. But that's hard work and I'm lazy. So let's look at d squared prime. Let's just minimize this thing. Still some chain rule involved, but a lot less than if we had the square root. When I differentiate this piece using the chain rule, I'll get 2 times 1/2 y squared minus 1 to the 1 times the derivative of the inside. Well, what's the derivative of 1/2 y squared minus 1? That's 2y minus 0, or just 2y. And then plus the derivative of this piece, another chain rule thing, that's 2 times y minus 4 to the 1 times the derivative of the inside, which here is just 1.
Excuse me, Is that 2y or would it just be y? Would the 2 cancel out?
We're looking here.
Mhm.
So, you're correct. Yeah. The derivative of y squared is 2y. The derivative of
Okay.
1/2 y squared is just y. Thank you. It's very nice of you to catch the mistake just before I let it cascade into bullshit. Nicely done. Yeah, but you're exactly correct. All right. So does everybody follow what's going on here? It's a chain rule derivative. It's not anything too crazy. And the big idea is that instead of taking the square root to get d alone and then differentiating, I say, fuck it, I'm just gonna minimize this thing rather than minimizing the square root of it. Because I get the same output either way. The square root will be minimized when the inside is minimized. Conveniently, these powers are both 1 now, so there's nothing terrible to deal with. We can just try to clean this up a little bit. 2 times 1/2 y squared would be y squared. Minus 2 times 1 is 2. And then I still have my y over here. And then here I have 2y minus 8. So altogether, this is y cubed minus 2y plus 2y minus 8. And those middle terms cancel. So I get y cubed minus 8. My critical numbers will come from setting this equal to 0. Adding 8 to both sides, we get y cubed equals 8. And then taking the cube root on both sides, the cube root of 8 is 2. So there's just one real number that satisfies that equation. It's the number 2. And now I can build a number lines. The number line here is technically for d squared primed, the derivative of the square of the distance. The only critical number there is 2. And I want to check and see that when y is equal to 2, I'm really minimizing the distance and not maximizing it. So if you plug in something to the left of 2, like 0, you get 0 squared minus 8, which is negative 8, which is definitely negative. If you test something to the right of 2, like y equals 3, you get 3 cubed minus 8, which is 27 minus 8, which is definitely positive. So we are decreasing everywhere to the left of 2, increasing everywhere to the right of 2. That means y equals 2 must be a min. Not just any min, but an absolute min. So the function d squared has an absolute min when y is equal to 2. And if the square of your distance is minimized, then the distance itself is minimized. This means d is minimized, or is minimal at y equals 2. But I still haven't found the point. I found the y value of the point where the distance is minimal. So to find the point itself, I need to say recall. We're looking for a point on the curve y squared equals 2x. So when y is equal to 2, we get 2 squared equals 2x, which means 4 equals 2x, which means x is also 2. So the point on the curve that is closest to the point 1, 4 is 2, 2. And we can illustrate this in Desmos. I'd like to do that before moving away from this. But before I do that, are there any questions about the individual steps here? Okay, then let's take a quick peek at Desmos. I think you'll like this. Here's that parabola, y squared equals 2x. Here's the ordered pair 1, 4. And I'm looking for the point on this curve so that the distance from 1, 4 to that point is as small as possible. Here's the point 2, 2. And here's that distance. Do you see that if I come over here, that distance is getting bigger? And if I come over here, that distance is getting bigger. This point is getting further from the blue point. So the point where that distance is smallest really is right here. As I go this way, it gets bigger. As I go this way, that distance gets bigger. And again, this is something I'm gonna have to see if I still have it. At one point, I made a little tool for this. It's still there. Yeah, here's a similar thing. So we want to find the point on the graph f of x equals the square root of x that is closest to the point 3, 0. This red point right here, I claim, is that one. And if you look at all these distances, they're all bigger. So it gets smallest right there, and then it gets bigger again. These sort of problems can be a little bit challenging to visualize. So I do really like this tool. I'll go ahead and paste the URL for this in the chat. I think it is probably also in your modules under the resources for this section. There we go. Oh. So that is applied optimization, right? Some of these problems are purely geometric in nature, but the majority of them are like real world word problem type things. I think we have time for one more. I have you guys till 3:15, right? Let's see if we can get one more little example. Look at something fun. Largest rectangle in the semicircle of radius r. Sure. Well, let me, I'll simplify this a little bit because we only have a few minutes. Let's find the area of the largest rectangle inscribed in the upper semicircle of radius 4. Let's do it like that. So here is the upper semicircle of radius 4, right? Semicircle just means half of a circle. This would be the point 4, 0. This would be the point 0, 4 up here. And I want to know, inscribed means, right, like the vertex is going to be along the vertices for the rectangle will be points on the semicircle. So there's a bunch of rectangles like this that I could draw, right? I could draw one like that, or I could draw one that's very narrow like this. The question is, of all possible rectangles like that, which one will have the largest area? I'm going to start similar to the last problem. I'm going to call this point here, where the rectangle touches the circle, x, y. And I'll also say, recall the circle above has equation x squared plus y squared equals 4 squared. Right, which is x squared plus y squared equals 16. And if you solve this for y, all right, here both x and y are squared. There's no like nicer variable to solve for, so I'll just solve for y. You'll get the square root of 16 minus x squared. Now, technically, there would be a plus or minus here, but that's for the whole circle. So if we're just talking about the upper semicircle, this is it. What that means is, if you take this and plug it in up here, this point is really x, well, it's y, and y is a point on the circle, so it's got to be the square root of 16 minus x squared. That's what y is. So this is kind of like our constraint. And the thing we're trying to maximize is the area of this rectangle. Now this height here is just y. This width here is 2x. And I know that y is the square root of 16 minus x squared. So plugging in this information from the constraint to this thing I'm trying to maximize, I get this. This is 2x times the square root of 16 minus x squared. In order to maximize this, I'll need to take a derivative. So a primed here is going to be a product rule thing, 2x times the square root. So I'll differentiate the 2x, leave the square root alone, plus leave the 2x alone, differentiate the square root. This is going to be 2 times the square root of 16 minus x squared plus 2x times. Now, when I come to differentiating that second part, chain rule stuff, that square root is a 1/2 power. So this is going to be 1/2 times 16 minus x squared to the negative 1/2. Subtracting 1 from 1/2 is negative 1/2 times the derivative of the inside here, which is 0 minus 2x, or just minus 2x like that. And if we put all of this together, that's 2 times the square root of 16 minus x squared minus, because this negative, and then 2x times 2x is 4x squared times 1/2 is 2x squared. So 2x squared divided by the square root of 16 minus x squared, like so. Next, we need a common denominator. I can put these together and find my critical numbers. So I multiply by the square root, right? This square root down here, root 16 minus x squared is my denominator. If I multiply this first piece by that square root over that square root, I get 2 times 16 minus x squared minus 2x squared all over the square root of 16 minus x squared. We can factor out a 2 and combine like terms. We'll have 16 minus x squared minus x squared. That's 16 minus 2x squared over the square root of 16 minus 1x squared. So your critical numbers come from setting the top and the bottom equal to 0. These would be plus and minus 4 from the bottom. And from the top, if I set this equal to 0, I get x squared equals 8. So x equals plus and minus the square root of 8 from the top. Now, plus and minus 4.
I'm sorry.
Sorry.
I think when you took the 2 out, where it's 16 minus 2x squared, shouldn't that just be 16 minus x squared?
This piece will be 16 minus x squared, but I'm also factoring the 2 from this guy. So I'd have 16 minus x squared minus
X squared. Okay, thank you.
You're good, you're good. So the plus and minus 4, positive 4 is over here, negative 4 is over here. If x is either of those, then the area will be 0, right? Because the height would be 0. So these guys are not of interest to me. The 2 that are of interest to me are these guys. So you can think of 4 as being over here and negative 4 as being over here. Those are the endpoints, and my area there is 0. So not worried about or interested in them. Negative square root of 8, however, and positive square root of 8, these are interesting. The top here factors as a difference of squares. And if we do that, we see that both of these are multiplicity 1 roots. So we can get away with just testing one number, and that number I would pick is 0. If we test x equals 0, you see this is 16 minus 0 over the square root of 16 minus 0. The 2 out front, that's definitely positive. And then each of these being multiplicity 1 roots tells me that each of those are negative. So we are decreasing, 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 increasing, 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 decreasing, decreasing, decreasing. This is a min. This is a max. So when x is equal to the square root of 8, this area will be maximized. And that max area I just have to go plug back into my area function is a equals, well, it was 2x times the square root of 16 minus x squared at x equals root 8. This becomes 2 times the square root of 8 times the square root of 16 minus the square root of 8 squared. Square root of 8 squared is 8. So this is 2 root 8 times the square root of 16 minus 8, which is the square root of 8. So that's 2 times root 8 times root 8 is 2 times 8, or 16. I think the pure geometry problems like these tend to be the ones that take a little bit more practice. It's sometimes, I think, a little bit harder to use your imagination here, because the real world stuff, you can actually try to picture the physical situation and develop some ideas. Here, you really do have to know the math. You've got to be comfortable, sketching the curve and knowing what the equation for that curve is, comfortable with the concept of distance from the previous one, comfortable with the concept of inscribed areas here. Those are a little bit abstract. So that's not something I would worry about running into on your exam, although you will see some problems in your homework set. As far as preparing for the test regarding this section, my advice would be make sure that you can solve most of the problems reasonably well. If you're having trouble with any of them, please don't hesitate to come by. Remember, on Wednesday this week, we're going to be doing just review for the test. So if you want to see any more of these, we can see them on Wednesday. Otherwise, bring questions from the study guide, questions from the homework, questions from anything we've done so far in the class. Wednesday is going to be your day, so we will do whatever it is you guys want to do on Wednesday. I know I've gone a few minutes over, so I'm going to go ahead and wrap up here. Is there any last minute burning questions you want to ask before I end the meeting?
So we are still planning on doing that test on Friday.
Yes, sir. Yep, exam 2 will be this Friday, and the review, we will spend Wednesday's class reviewing for the test.
Lovely.
Same policies as always, of course. If you're feeling your back against a wall, you feel like you need more time or something for the test, I can move you into the makeup group. Just be aware that after the test, of course, we're going to start studying new stuff, and delaying one test has a cascade effect on the next one. So if you're feeling that way, I would much rather you let me know and get a little bit more time preparing for the test. I'll put you in the makeup group. Please do that. Don't cheat. If you're feeling stressed, I would much rather give you a little more time. All right. Okay, if we're all feeling good, I'll go ahead and end the meeting here, and I'll see you guys on Wednesday. Make sure to bring questions, problems, things you want to look at on Wednesday. It'll be your day, and then the test is Friday. Take care, guys.